Well, I was hoping to do this last night, but that didn't happen. So better late than never. And then after lunch, I'll get to working on my presentation of one of the papers. All right, this week we have, again, more core content about static and dynamic analysis. So we had type systems last week, and now we have some static analysis and some dynamic analysis. And so we have this Permchecker paper from OOPSLA and this incremental analysis paper from PLDI. So what is a specific thing, like the Permchecker paper is a definite thing that you do to check garbage collection algorithms that exist, or implementations that exist. And the other paper is more of a meta paper. It's like, okay, here's this technique that you can use to improve other things, better tools for analysis. Let's briefly summarize both these papers. So the garbage collection paper, Permchecker, this is an OOPSLA paper. Note that it looks longer than it is because it's single column as opposed to the PLDI double column format. But it still has quite a bit of content. The PLDI papers also have a lot of content, but they look shorter. So this is about typestate. It's an application of typestate. Typestate is now quite an old idea. It's from 1986 and a Strawman-Yameni paper. And this is a concept that should be useful, and there's been a lot of research that's used typestate. And so it was like a core part of my PhD, for instance. And Sofia Drassopoulou did a bunch of research on dynamic typestate in FICL. It doesn't, unfortunately, seem to have caught on beyond research typestate, which is really kind of unfortunate. Sometimes these things take a while, right? So garbage collection was a very old idea, but until Java caught on, no one was like, well, we can actually do garbage collection. And ownership types have been around for a while, but only recently has REST made them viable. So it is a thing that sometimes programming languages research takes a while to become actually used. Hopefully it'll be the case with typestate as well, because I think it is useful. It's just that most of the time languages don't actually support it. And the idea is that you have types, which we know about, and part of the type is a dynamically changing state. And so the canonical example is you have a file and it's open or closed, and you can only do certain operations on it when it's in certain states. Like you can only read from a file that's open. Okay, the other part of the context of the GC paper is that memory management is hard. And so it's a well-known domain that's highly intricate and it's hard to debug. There was some sort of joke that I tried to find, like I broke my tools using my tools, but I didn't have the right keywords, and so I failed at that. Anyway, part of it is they point out, look, you got this garbage collection thing, and you can't debug it because you have no tools to do it. It's just hard. So here's a dynamic analysis approach that gives us some information about what the garbage collector is doing. And so there's some annotation, and then from the annotation, there's instrumentation generated from the annotation, and it tells you when the garbage collection code is doing the wrong thing. I really like this paper. It has many things that I like. So it leads right away, like the first sentence is an example. The technique is conceptually not that hard, although there's a lot of implementation details, and you try to read what it does specifically, and it's like, that's kind of hard. But conceptually, it's like, okay, you have the heap, it's divided into various parts hierarchically, and then you can only change the parts of the heap that you should be changing in particular. So only some accesses are okay, and only okay by certain parts of the garbage collector. So only some accesses are okay by some code at some times. They implemented the annotation and the dynamic binary instrumentation for their approach, and they said it's hard to test it because most garbage collectors don't have many bugs. So there's a false fault injection to find actual issues. I couldn't quite remember if they found actual bugs. They back tested, which is kind of okay, but not as compelling as finding actual bugs to find some bugs. One thing I also liked about the paper is they were pretty upfront with known limitations. That inspires confidence in their scientific integrity. Of course, they have blind spots too, and we should, in general, expect that. Okay, that's what I have to say about the garbage collection paper. Now about the other paper, the incremental analysis paper that I will be working on a presentation on. Okay, so Datalog. Datalog is a thing that I actually set out to learn last summer as I was writing a paper, which I'll also post to the thread as well, which used both a static analysis approach and a Datalog approach. And so the idea here is that you specify constraints on what you want your analysis to find, and you say solve, and then the Datalog engine goes and solves your problem, and you don't have to imperatively implement the thing. You just have to specify the constraints. And it works, for instance, for pointer analysis. They have other examples where Datalog is used as well. And their problem motivation is real-time IDE results, right? So right now they're like, okay, so IDEs do things ad hoc. IDEs and other tools, like Infer is not an IDE tool, but it runs pretty quickly because it runs on a whole program. And if you try to run the whole program, not incrementally, it'd be too slow. And the question is, can we generalize the approaches that the IDEs do to something that works? You have any analysis and you're like, okay, here is a dynamic version, or here is an incremental version. That would be great. And so what they do is, first of all, they have, well, when is incrementalization infeasible? And so they do an empirical study of that based on their analysis of incrementalization. And then they wrote an existing solver, IncA, incremental, but they made it better. And so they have the ladder technique with 3Ds. And so the main things they address are, well, sometimes IncA does too much unnecessary work, and sometimes it has too strict monotonicity requirements. And so they have a novel aggregation semantics. We won't talk about it that much. We'll just show some examples, and that'll be enough. And so the idea there is never forget anything, but don't talk about the things that you would otherwise have forgotten. And so they find results that IncA with their thing, without their thing, took tens of seconds on some things, which is too slow for interactive use. And with their thing goes to 10 milliseconds most of the time, almost all the time, which is fast enough. So there is formal semantics in the paper. It's actually relatively short in the paper, but what we'll do when we talk about it is we will actually not talk about that at all. We'll just talk about the motivation, the examples, and the result. And that is kind of the approach that we want to take in this class. We're not investigating the papers at the depth of the actual nuts and bolts of it. That would be too much and would take more than 1 week to learn. Okay, so 2 papers this week. I think they're pretty intricate, but they're not the hardest papers that I've assigned. Sometimes I just assign something that's way too hard. And I think these should be tractable. So, well, I will prepare my talk, and I'll look forward to the talk, and we will talk about them tomorrow. All right, see you then.